Hello, everyone. This is a demonstration for the online exercise covering Chapter 10. And Chapter 10 is about computing variance and covariance matrix. So in our previous example or previous chapters, we covered the calculation of efficient portfolios, and we need individual stocks within to be selected into the portfolios. And each individual stock has their expected return and the standard deviation or variance to measure the risk and the return. And we also need, because we have multiple individual stocks, so we have an asset portfolio. So that means that we also need to consider the co-movement between each pair. So combining the risk structure for all the assets, we call that variance and covariance matrix. In our previous example, these variance and covariance matrices are provided by the questions, but in practice, this should be calculated because it is derived or it is calculated based on the stock's return. So we're learning that. And then apart from that, there is also correlation matrix, which is a simple deviation from the variance covariance matrix, also capturing the co-movement between each pairs within the portfolio. And then finally, we'll cover global minimum variance portfolios. And there's a side note here in the chapters. Apart from the measures that covered in our lecture, there are other measures as well to calculate variance and covariance matrix. So the number may be slightly different from the sample variance covariance matrix that we learned in class. Basically, there are some criticisms about the variance covariance matrix that people calculated, the very basic one. So to correct some biases or correct for some limitations, to overcome that, there are other ways of calculating the variance and covariance matrix. So these are provided in the textbook. All right, so calling for the variance and covariance matrix, we are looking at this n by n square matrix here. It is a symmetric matrix, and we have covered in the previous lecture. So the diagonal elements here are variance, and all elements on the apart from diagonal elements are covariance between each pairs. So 1, 2 means the covariance between asset 1 and 2. 1n means the covariance between asset 1 and n. And sigma 1, 2 equals to sigma 2, 1. So sigma here is sigma 1, 2 here represents the covariance between 1 and 2. Sigma 1, 1 here represents the covariance between asset 1 and asset 1. In other words, this is the variance. So the covariance of yourself is therefore variance. So this variance and covariance matrix captures not only the risk of the individual stocks, but also its co-movement between all other stocks in the portfolios. So we use sigma, we use S, or we use the big sigma term to denote this variance covariance matrix. So to calculate sample variance covariance matrix, this is our formula. So there are other formulas to calculate variance and covariance matrix. Again, it is if you want to be aware of other measures, the text will cover it, and there are examples as well. So going back to the basic measure, sample variance covariance matrix. So we are assuming that there are n different assets over n different periods. So we'll have, for example, n different stocks, 100 different stocks, n could be any. We want to generalize our formula so that it can apply to any n. So over n, different periods. It could be 10 months, 10 years, 10 days, so m different periods. And we are trying to write the return of SI in period T as RIT. So I represents the stock, specific stock, and T represents the time when this return was realized. We write the mean of the return, which means the average of the return of SI as return in each single period divided by the number of periods. So this is summation of RIT, and T is going from period 1 all the way to period M. So sum all the individual returns in one single period and then divided by the number of periods. And the time interval should be the a fixed time intervals. So if you're not using a daily return added to a monthly return added to an annual return, if you choose to use monthly return, then each period is 1 month. So the interval between each period, the time gap should be just 1 month if you choose monthly return. And then that will be the mean. We use R bar to represent that. So we'll want to summarize the time series into one average. So that summarize that information from a time series data by the average level of the return. And then we want to start it to calculate the covariance between each pair. So we're assuming we're using SI and SJ as an example. So I and J is basically one SF1 and SF2, could be SF1 and SF3, SF1 and SF4, and so on. So sigma ij equals to, it is basically a notation for covariance between I and J, between SI and SJ. And then that equals to 1 divided by number of periods minus 1. So basically this is scaling of the sum product of deviation from mean. So you remember this R bar is the average return of individual stocks. So you're using each single periods, subtracting the average for this individual asset I, so deviation from mean. So for period 1, so deviation from mean for asset I times deviation from mean for asset J. So, and take the products between these two. So in period 1, if the asset I deviate from its mean by a lot, and asset J deviate from its means by just a small amount, then this whole product will be not a big number because it's a large number times a small number. So it's going to be not going to be a large number. So then when you take the sum, if each period is like that, the sum is not going to be a big number. So that means the co-movement between I and J is not strong. But if each period, when one moves quite a lot and the other asset J also moves quite a lot, this product will be a very big number. So then that means that the co-movement between I and J is gonna be strong. So in the opposite scenario, like in a negative correlation scenario, so that means one move up, another one move down. So then this will be a negative number. The product will be a negative number. So when you take the sum, it will become because there's negative numbers out there, then the sum will become a very negative number or a very small number. So the co-movement can be a negative number as well. So this basically summarizes the co-movement of between I and J by each period, and then take the average. So because it divided by the number of periods. So the way of calculating it in Excel, so here is it. We're gonna calculate the deviation from mean first. So this is our A matrix. So it's assessed return. We call it assessed return. It's nothing too fancy. It's just the deviation from mean. And then we transpose it. So take A transpose. So the sample variance covariance matrix formula by this measure is A transpose times A divided by n minus 1. So usually we'll obtain data from obtain the stock return data or stock price data. So we can get it from Yahoo Finance or Bloomberg. So the example that we are looking at here is a 10 stocks example. So there will be 10 different stocks and the final stock in this final column. So this is not the final stocks. This is additional. So I think 1, 2, 3, 4, 5, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So yeah, so up to Exxon Mobil. So this will be the 10 stocks. So S&P here is serving as the market return, the benchmark return. So we're gonna turn price data into return data by calculating the percentage rate. By calculating, I think here is we're using log return. And then we'll take the average because later on we'll calculate the deviation from mean. So the next assessed return time series will be the deviation from mean. So that's why we need to fix the average, the cell here, because there's only one single mean for each stocks. And then we'll just following the formula here. So taking A transpose, so transpose A, transpose the deviation from mean, and then take the product. So A transpose times A. So we're doing matrix multiplication. A transpose times A and divided by n minus 1. So there are 60. So there are 60 returns, 60 periods here. So it's 60 minus 1, which is 59. Right, so I'm going to show you how to do it in Excel. So the first page here, the first sheet here tells you the price for the 10 stocks in each single period. So the current frequency that we're using is monthly. So the first day of the month or the first trading day of the month. And then we have a market cap here. So which for your information. So therefore, so this, the return, we're using log return. So there is another way of calculating return, which is percentage return. So we're using log return. This will be log return of today's price divided by yesterday's price, and that's it. So I'm gonna drag it all the way here and double click. So the mean is here. So automatically calculated is just the average of the above percentage return. And then next, we'll be calculating the deviation from mean from the return time series minus the mean. And I would rather fix the cell, but not gonna fix the column. So I'm fixing the row, but not fixing the column because I wanted to roll the formula to the right. So enter. So deviation from mean and looking good. So this will be here, good. And then double click this to populate the formula. So good. So the mean is keeping it the same. So for each period, we're subtracting the return from the mean. And the mean is always this line. Right, so next is calculating the variance and covariance matrix. So our formulas looks like this. I'm copy the formula here. So we will need matrix multiplication, and then need to transpose the deviation from mean. Transpose this. And then close the bracket, comma, A transpose times A, and close the bracket, divided by number of periods, which is 60 minus 1. Okay, so that will be question 1. So this is following the formula here. So A transpose times A divided by n minus 1. So as you see it, so we're doing this, we're calculating the variance covariance matrix in multiple steps here. So is there an easier way to do that? Yes, it is. We can write it into the algorithm so that we don't need to manually expand our calculation in multiple cells. So we can just do it in one step. So we're defining a user-defined function, which is called variance covariance. And we end the function here. So this will be a user-defined function. And then in the middle point, in the middle block, this will be our definition for calculating the variance covariance matrix, which we can solve it ourselves by question 1. We have already did it, solve it ourselves. We just try to write the calculation in the algorithm. And then we need to define as a I and as a j. So it's an integer. So define I and j so that Excel know what we mean. And we need to define number of columns. So number of columns equals to column count. So which means Excel will count the number of columns for the input. And then number of rows will be calculating the number of periods here. So in this case, we have number of rows equals to 60. So number of periods is 60. So we need to count the rows as well. So the R and G here is the input. So input should be the return. So that's why the number of column means number of stocks that you are calculating. And then number of rows means number of periods of return. So RNG dot row dot count is it's a function that Excel VBA can it already knows that okay, so if you write this, I'm gonna count the number of rows in this input. And then we're gonna define a matrix. So this matrix is double, so the value within this matrix will be number. So then we'll start the loop. So for I equals to 1, all the way to number of columns. So if we have 10 different assets, so then I equals to 1, that is the first iteration. So I equals to 2, that will be the second iteration. And then we write another loop. So because we want to calculate basically the variance covariance matrix structure looks like this. So it's first starting from asset one and asset one, the covariance between 1 and 1, the covariance between 1 and 2, the covariance between 1 and n. So we just need to let Excel to calculate, write a loop and let Excel to calculate when I equals to 1, then I equals to start with that, and then calculates the variance, calculate the covariance between 1, 1, 1, 2, all the way to 1, n. So J represents the second number here. So that will be, so after it runs all the J's, then we have finished the calculation of the first row. Then move on to the next row, that will be I equals to 2. So then it will finish J from equaling to 1 all the way to 10. So then finish the second row, then move on all the way to I equals to 10. So if we have a 10 different assets in the portfolio. So the reason that we need to calculate it one by one is that we want to utilize the function that Excel already has. The VBA also can read. It is a function building the Excel and also building the VBA. So it's called covariance function. The covariance function cannot calculate a matrix for you. It can only calculate the covariance between two pairs. So that's why we need to write a loop so that it loops over all the available assets here. So then we put it into the location into this matrix. So then run it all the way over from 1, 1 all the way to n, and then we output the variance covariance matrix, make it equals to the matrix. So that's the formula, and this is what we are trying to do in question 2. We're trying to calculate variance covariance matrix using Excel VBA. So I'm going to copy the formula here. So copying here, opening Excel VBA. And copy the code here. So this will be the user-defined function for variance covariance. I'm copying the name of the function. And you can go back to the Excel file to use the function. So here equals to this, and the input should be the return. So the covariance and the variance is the variance of the return. Okay, so the covariance is the covariance of the return between two assets. So enter, and that's it. So you may wonder, so let me just do one more thing here. So because this is a matrix and it tells you the structure and the the relation inside each pair. So we use, I think in the code, we use covariance, the Excel's covariance calculation. So let's do the covariance between X and ExxonMobil. So I'm going to use X return and then ExxonMobil's return and enter. I need to turn this format into general. And there you go. So it's exactly the same. So these two. So we're just using the individual function, write a loop that use this individual function and loop it over each pairs. So it will be a 10 by 10 matrix here. So next, we can also use the VBA function to calculate the correlation. And if you can recall, So correlation is basically the covariance divided by the sigma standard deviation of SF1 times standard deviation of SF2. So it's covariance scaled by the product between sigma 1 and sigma 2. So standard deviation of SF1 and standard deviation of SF2. So it's just covariance being scaled. So you will, therefore, essentially they are all measuring the same thing. So copy it in the VBA. So I have correlation matrix. I also would like to copy the correlation matrix triangular, which is in the next slide. So I'm copying it down here. So I have two user-defined function here. So one is enough. So I'll show you why I copy the next correlation matrix triangular in the example in classic exercise. Right, so here I'm going to calculate correlation matrix equals to the return and enter. So as you can see, this 1, 2 equals to 2, 1. 1, 3 equals to 3, 1. And here, this equals to this. So it's symmetric. So this part, this upper triangle, is exactly the same as the lower triangle here. And the diagonal element, they are all 1 because the correlation of one SS with exactly itself is 1. So therefore, the information on the lower triangle will be redundant. So essentially, we just need the upper triangle. So that's why we have correlation matrix triangular to make everything more efficient. So show everything in a more efficient way. So it will only show the upper triangle. So the reason in the code, if you look at the code, it just tells Excel to stop the loop at a specific point so that it no longer calculates the lower triangle. So it has like a stop order there. So everything else are the same as the algorithms that use for calculating correlation matrix here. So it's still using the covariance function in Excel to calculate each pairs of stocks. So this part is just an alternative way of showing the correlation matrix. All right, so final part is we want to calculate the global minimum variance portfolio here, so which has the lowest variance. So it is the efficient portfolio, but there is only one efficient portfolio on this point that has the lowest variance, and we call it minimum variance. So we need to figure out that using the formula. So the formula is we need a unit row vector multiplied by S inverse. S is the variance covariance matrix. So this will be matrix multiplication of one unit row vector times S inverse. And then this will do two matrix multiplication. First is one, the unit row vector times S inverse. And then the product of these two times one unit column vector. So that will be the solution for the weight of the global minimum variance portfolio. So X all the way here from 1 to X1 all the way to Xn represents the allocation to S1 all the way to Xn. So we're going to implement this formula. And to do that, we need these two user-defined functions so that we can generate a unit row vector and unit column vector. So copy it in Excel and paste it. So paste it down in Excel. All right, and go to our exercise here. Let me try if unit row vector works. So unit row vector, and let me show you how they work. If I put 5, oops. All right, so I need to turn all these into general. Okay, good. So if I put 5, then there will be 5, 1 in one single row. So that is unit row vector. Let me play more. So if I do 10, it will put 10 different ones. So that's unit row vector. If I do unit column vector, 5, then it will be one single column with five different cells, and each value equals to 1. So that is what we call unit row vector and unit column vector. So then we'll just need to implement the formula. So the formula, let me copy it here. So formula is coming from this. So we need to do, let me do this. Copying this. And here. So I'm gonna just switch the order. Comma, and change this to row. And I'll do matrix multiplication. Here, I have unit row vector. And minus, comma, close the bracket here. And I need this. And unit column vector, that is right 10. And here, and I don't need the last bracket. Formula is missing an opening or closing parenthesis. This. Okay. Here. All right, I got it. And that's outputting the solution for the minimum variance portfolio, the weights allocating to each single stocks, and we output it in one single row. If you want to output it in one single column, you can do that by transposing this, or you can just slightly change in the formula and it's going to output it in one single column. All right, and then calculating the return, portfolio return of the global minimum variance portfolio. So you can do matrix multiplication. Let me see if, yeah, you can do matrix multiplication of the weight times the return. We need to transpose it. Oh, let's see, should be okay. Okay, good. That's one way of calculating the return. You can also use sum product. It's basically weighted average. So weighted average is some, you can use sum product to calculate weighted average as well. Enter, it should gives you, oops, should be K. Should give you the same thing. All right, and then variance goes to matrix multiplication, and transpose. Transpose these here. Times variance-covariance matrix, close the bracket, comma, suppose to close the bracket, and finally is the X. All right. So let me check the formula. Let's see. So I'll do transpose here. So the reason I do that is here, the formula. All right, so the formula we covered last time, it's supposed to be X transpose times S times X. And our X, the weight, should be a column vector. If I already put it into a row vector here, that means I have already transposed it. So you either use this one or to transpose it so that you exactly follow the formula here. You can. So I can do transpose. But I'll need to change this to here. And do this. Okay, so then this way it exactly follows this. X transpose times S times X. All right, sigma will be easy, square root of the variance. Okay, so that's it for the exercise.